So SiC solar cell, so SiC is a direct band gap semiconductor that strongly absorbs light. What I mean right here is that it had a high absorption coefficient and has a tunable band gap from 1 eV to 1.7 EV by adjusting the gallium content in SiC. And in the literature, the SiC single junction solar cell have reached efficiency higher than 20%. So it is a good semiconductor material for a semiconductor. So we have come up with a model of a SiC single junction solar cell. So this is the structure. These are some simulation results, which are JB curves at different molar fraction. What I mean by molar fraction is just the gallium content and EQE. And to validate our model, we could achieve results which are similar to what we can find in the literature. So then we move on multi-junction solar cell, which is the main subject of our research. So what they are, they consist of subcells connected in series through tunnel junction, and each subcell will have a specific band gap, which will make that each subcell will absorb a specific portion of the solar spectrum, which means our solar cell is absorbing the solar spectrum more efficiently. So the current produced by the whole device will be equal to the current produced by the limiting subcell, which is just the subcell that is producing the least amount of current, and the voltage will be equal to the sum of all the voltage since they are connected in series. So here the germanium has some disadvantages because it has a high cost, it's a high cost material, and it overproduces current compared to the two other subcells, and this extra current will just be dissipated as heat, which will decrease the performances of our solar cell. And I also want to mention that since multi-junction solar cells are high efficiency, we want to use them under light concentration. And when we use light concentration, the JC will increase linearly, the VOC will increase logarithmically, and the efficiency will increase logarithmically. So the main challenges in our simulation is the gas-SiC interface, because we want to grow gas which has a zinc-blende crystal structure on SiC which has a chalcopyrite crystal structure. I just want to mention that this has already been done experimentally by research groups. And okay, so here we have the last constant of SiC as a function of molar fraction, and this is the last constant of gas. So as you can see here, they are a lattice match at a mole fraction of about 0.71. And our SiC subcell that we want to replace from germanium in the triple junction solar cell, we want it to absorb the same portion of the spectrum, which will be at a band gap of 1 eV, which means at a mole fraction of 0. So we want the main part of our SiC subcell to be at a mole fraction of 0, but so we have a gas emitter here, but at the interface we want SiC to be at a mole fraction of 0.71 and then vary the mole fraction to 0. So here we'll have a gradient region where we vary the mole fraction, and strain due to lattice mismatch growth of gas on SiC will result in threading dislocation density. What is threading dislocation density? It's just defects that will propagate through the device. And the way we model that is by affecting the non-radiative recombination lifetimes, since these are defects. So some simulation results. So these are EQE. So this is the EQE of the top subcell, the middle subcell, and the bottom subcell. And as you can see, they all absorb a specific portion of the spectrum, so a specific range of wavelength, and it will all decrease with TDD. This is JB curves as a function of TDD. So again, the performances of our solar cell will decrease with the TDD, which is just threading dislocation density. So here are the JB metrics. So JSC, VOC, fill factor, and efficiency as a function of TDD. And what we can see here is that the performances of our solar cell stay constant up to a certain target TDD. So what we want to say here is that if someone can grow these types of this kind of design with the triple junction with a 6 bottom subcell, you can obtain quite good performances. So this is at 1 sun. With no TDD, we would have efficiencies up to 37.5%. Then 1 in the 6, which is our target TDD, we could go up to 32.8. But then past this point, the performances starts dropping abruptly. So now we want to study this with concentration. So this is efficiency as a function of concentration at different TDD. What we see over there is that at really high concentration, which are like 1,000 suns, we are producing really huge amount of currents. And when these big currents are passing through the top contact, we need to include series resistance in our model. But we still have a maximum efficiency peak at a concentration of about 300 suns. So at 300 suns with no TDD, we have an efficiency of 44.7%. And at TDD, this is our target TDD, efficiency of 40.2. Just want to mention that the world record at 364 suns is about 41.6. So we can achieve similar performances as the highest efficiency solar cell that we can frame now with a reasonable TDD. So in conclusion, we have modeled the performances of a multi-junction solar cell consisting of InGaAs and SIGs instead of germanium. With that model, we have studied the effect of threading dislocation density, and we could obtain comparable results to standard InGaAs germanium technology. But by using SIGs, we would potentially have a reduce of cost. Thank you for listening. I hope you enjoyed it.
Do you have any questions for Frederick?
So you mentioned that the efficiency for the world record is 40%. So just for comparison, what's the most efficient product out there commercially?
It is exactly.
Oh, okay.
This is a triple junction with dilute nitride, and at 364 suns. So these are the most efficient solar cell at this time. Of course, this is just a model, but we have included the growth challenges by including TDD. So we would say that like at no TDD we obtain a better efficiencies, but this is just a model. But if we say if you can grow these type of design with a TDD of 1 to 6, you can obtain similar results. So this would be a novel design that could potentially be on the market one day. Any other questions? Yep.
Is there an experimental side, not you, but in your research group in general, or do you just model and?
So we have collaboration with other universities because we are in University of Ottawa in our research group. We are more a modeling facility. So that's what we do. We have a modeling software and we model different types of design. But we have some collaboration, for example, with McGill that are growing this solar cell and then send it to us. We try to obtain the same, to model what kind of design they have come up with, and then we can kind of find what are the carrier concentration, what are the doping levels, and everything like that. So no, we're not growing these types of designs. This is just a model, but we're trying to include the difficulties in growing such a device in our model. Any other questions? Okay, so thank you for listening.